All right, so with this question, we're trying to use the quotient rule. So that means that we are going to split up this radical into several little radicals. So another way of thinking about this is we're trying to deal with this radical piece by piece. So we will have in the numerator the square root of 11, the square root of n squared, over the square root of 4 square root of m squared. So we're trying to deal with each of these individual pieces. Now, as we deal with each individual pieces, the square root of 11 is a prime number. So square root of 11, there's nothing to simplify there. So then you go to the square root of n squared. Now, one thing to notice is that the index here is 2 and the power is 2. So whenever that happens, the index and the power will cancel. And you can see this if you think about how we reduce the square root of n squared. What we do is we say, okay, we have an understood index of 2. We convert it, because it's a variable, into a division problem where the division problem tells us the powers that are on n. And so here, when I take 2 divided by 2, I just get 1 with a remainder of 0. So that tells us that the square root of n squared just becomes n to the first power. Again, this 1 tells us the power that will be on n, and so we'll have n to the first. Now, keep in mind, the square root of 11 is staying as a square root of 11. All right, this is over. Now, the square root of 4 is a perfect square. And you can see this when you take 2 times 2. You would then say, okay, one group of 2's outside of the radical, because we have one copy, one grouping outside of the radical. So that gives us a 2. Then for our square root of m squared, again, the understood index is 2. So we will take 2 divided by 2. That gives us 1 with a remainder of 0. So all of this 1 with a remainder of 0 is telling us the powers that are on the base of m. So that tells us that we have m to just the first power, no remainder, so m to the first. So that is our simplified answer.